Thanks, Jesse. Yeah, so today I'm going to be giving you a brief overview of the magnet design code Radia, and then run through a little demo of how you can build up a basic accelerator magnet in the Sirepo interface for Radia. So a little bit of background material on the code. Radia came out of the light source community and was originally used primarily for modeling insertion devices, though it has a number of nice features and properties that make it very attractive for modeling just about any sort of magnetic device you'll find in an accelerator and applications beyond particle accelerators. Internally, Radia is using a semi-analytic approach, a volume integral method. And this has a real nice property in terms of the solver, that you don't have to mesh up the entire simulation domain like you might in a typical finite element code that's often used for these magnetostatic problems. And so you, in fact, just have to be able to segment up the magnetic material in your design only, and then you can, after the solver is run, measure the fields anywhere in free space. So this can really cut down on the runtime for the solver when compared to some other methods. And then another nice thing important for our example of electromagnets today, Radia does handle linear and nonlinear relations for both isotropic and anisotropic materials. In terms of how the code is actually implemented, the code base is entirely open source. You can find it on GitHub if you want to take a look at that. All the core routines for the code are implemented in C++ for speed. And there are portions of the code that are parallelized, namely the interaction matrix construction, which I'll talk a little bit about here in a second. And also any of the field measurements are also able to be run in parallel, and that's implemented through MPI. In terms of actually using the code so to set up geometries, run the solver, and analyze results, there are three options for interfaces currently. You can use Mathematica, Igor Pro, or now Python is the most recent one added in the last couple of years. And Python is also the only option, I should mention, if you want to make use of those parallel capabilities. If you want to try out the Python interface, I'll mention we do have a Jupyter server on Sirepo.com where the Radia version of Python is pre-installed. So you can log into that and get started in a Jupyter notebook or in a terminal window just right away. So just at a real high level, they run through the method that Radia uses to actually find the magnetization in fields. So it's going to break up all the objects in your simulation into uniformly magnetized volumes. So generally just polyhedra, like the example shown here on the right. And then you can calculate the field at any point in your domain based upon an interaction matrix Q here and the matrix of magnetizations of all of these volumes. And so one nice thing here, the interaction matrix is really just a geometric quantity that illustrated down here. These are the actual equations that are used for these calculations, and these only depend upon the positions of the volumes and the orientation and sizes of the faces making up those polygons. And from that point, you can use an iterative solver to actually relax these matrix equations and find the actual magnetization based upon excitation from external current sources you might have and the interaction of these magnetized volumes. So the example I'm going to run through today is that of an electromagnetic dipole commonly used in particle accelerators. And if you're not familiar with those, a couple of examples here just illustrated on the left. These are commonly used as steering magnets. So for instance, at a ring, like at the Fermi Lab accelerator complex shown up here. The dipoles are spaced throughout this ring to keep steering the beam and keep it on this circular orbit. You can also use dipoles in a lot of other applications. Here are a couple installed on a beamline down below, these green boxes. These are the first two dipoles in a 4-dipole chicane that's being used to manipulate the longitudinal phase space of a passing charged particle beam. So the geometry you're actually constructed, you'll see, is going to end up looking something like this cross-section shown here. So for a electromagnetic dipole, you have a yoke structure shown in blue. It's going to be made up mostly of iron. And then you'll have two poles sticking down into it, kind of outlined here. And you're going to have coils, current carrying coils, wrapped around these poles. If you want to see what that looks like in a full picture of that, down below here, if the real dipole, you've got the coils actually wrapping around the poles. And so that current is going to excite magnetization in the iron, and you're going to actually induce then a magnetic field across this gap. And so if you have charged particles, say, entering the page, that V cross B force is going to deflect particles to the left or to the right in this uniform magnetic field. So kind of a motivating problem here is a question always about the field quality in a dipole. And there are a lot of different ways that you can look at this and measure this. We're going to take just one simple case here of the field quality on a line running parallel across the gap in our poles. And so you can imagine that in the center of the pole, where you essentially have these flat planes from the pole, that the field is going to be fairly uniform vertically, but as you get out towards the edges, the field is going to start to fall off in strength, at least the vertical component will. And so this can be undesirable. Ideally, you'd want this field to be perfectly uniform all the way across. And so, of course, there's an easy solution here, just make your poles infinitely wide, but that's not really practical from an engineering or cost perspective. And sometimes you may want to have a fairly high aspect ratio dipole so that your gap is going to be about on the order of the size of the width of one of these poles. And so that's the case we're going to look at today. So to actually get a quantitative measure of the field quality, you often look at the field quality measured on, well, in this case, on a line. So you've got this by term measured in x, so running parallel to our gap, and then we subtract off the peak field at the center of our gap, and then normalize by that same field to give us the deviation on a line. And you can see that plotted out here up top for just a simple case that we're going to see here in a few minutes in Sirepo, where we've plotted the field deviation against the fractional gap distance. So just our distance in x divided by the total width of the gap. And then these gray regions, the light gray corresponds to a field quality of 1 part in 10 to the third, and the dark gray is 1 part in 10 to the 4. So you really only have a few percent of the width of this pole face where you actually have really high quality uniform field. So we're going to look at first constructing this simple case where you might not have really good field quality, and then we'll look briefly at how you might start to improve this by making some modifications to the design. So I'm going to jump over to a browser window here. If you want to follow along, this will all be on sirepo.com. When you get to Radia, you would just go to supported codes and click this drop down, and Radia is down here. For now, I'm going to jump into my environment in Sirepo and go ahead and start a new simulation. I'll just give it a name dipole and leave the rest of these settings on their default and hit save. And this will start up a new environment here. So it drops you first up into the design tab. You can see that indicated up here in the top right. And this has just a series of cross-section views in 3 different planes. So we start out X, Y. You can switch this just by clicking on these buttons up here on the left. I'll go back to XY since that's going to correspond to that cross-section view of the magnet that we started out with in the PowerPoint slides. So in terms of actually building up your magnet, there are a few options just for basic shapes. You can see up top here, and also a few common compound shapes that you might encounter, particularly in accelerator magnets. And then finally, the other options here on the right, this extruded shape we'll see in action here during the second part of this demo. And there's also an option to import STL files. So this is a common CAD format. If you already have a magnet designed in some other program and want to import it into Radia, you can use this. For now, we'll get started building our simple design, which is just going to be a series of these cuboid elements. So I'm going to drag and drop a cube into the work area here. We'll call this pole, and then go to geometry. And we've got to set the center and the sides of our pole. So already got all these numbers there. Just have to enter them here. And then also set a segmentation. And so these segmentation numbers get back to talking about how the solver operates. These will be our uniformly magnetized volumes. In this case, we just slice it up uniformly along each axis and give some number of segmentations. And so if you have a field that's changing very rapidly, in some area, you might want to set a lot more segmentations along that axis. In this case, I'm going to keep the number of segmentations a little bit low. You might want to set this to be a little bit more segmented if you wanted a completely accurate answer. But this should be well representative of the qualities of the magnet and will run pretty quickly, which is obviously good for a demo here. All right, so let's also now add in the top of our yoke. And set the numbers for this. And also you'll notice that I'm also setting a distance in Z. This is going to be the length of the magnet along that beam axis out to 1 meter. And we're making this a little bit larger than the cross-sectional size, just because we're primarily interested today in the quantities in the center of our magnet. So we can ignore any edge effects that are also going to occur at the entrance and exit of the magnet, just like on the sides of the pole, by making this relatively long compared to our width and height. We'll segment this piece also. And now we just need to add in the leg of the yoke. Okay. So that is all the iron sections of the magnet. You'll notice it doesn't look quite like the picture yet. This is really just the first quadrant. And we're going to exploit the fact that we've got some symmetry here to not actually construct the full section. We're just going to tell Radia about these symmetries, and it will make use of those to speed up the solve by not having to discretize extra magnetic material. So I'm going to go ahead and drag and drop a group. We're going to just apply the same symmetries to all these. So we'll group all 3 sections together. And we'll call this group dipole. And I'm going to go up to transforms here, and then drop down, select symmetry. The symmetry is going to be defined in terms of the vector perpendicular to a plane and a point where that vector is centered. So this first symmetry will just be across our vertical plane. And then you also need to set how you expect the field to interact at that plane. And so, of course, this is running up and down this line here, you can see. So our field should be running parallel to this into the pole face. So we'll change this to parallel. And then I'll add in our symmetry across the horizontal plane. Change this vector to be vertical. And of course, the field is going to be going through this plane. So we'll keep this perpendicular setting. And there we go. So now this should look a lot like that picture. We just need to add in the coils. So we'll go up here to field sources, drag and drop in a racetrack. And then we've just got a few more numbers to enter here. This one coil, set its center. And then the full length of the magnet, and then be across the full width of the pole. We're going to make it not quite the full pole height. And then we also need to set the inner and outer radii for the bends and the coils. And then set an appropriate current density here. Oh, and we'll also want to apply a transform to this. We're just creating the top coil We can again use a symmetry now to set up the bottom foil. There we go. We can just check this if we want. We're going to look in another plane. You can see now the top of the magnet with the ends of the coil sticking out on either side here. So all that looks good. And now we can go up to the top right and select visualization. And wait a little bit here, we can take a look at a 3D rendering of the magnet we've just built up. Let's just look down the z-axis, and this is the way the beam will be going. You can see, zoom in here a little bit, the poles and the coils wrapping around. And then, of course, you've got all these are broken up into these rectangular blocks. And this is just, again, that segmentation for the solver purpose, and not anything you would expect physically when building up the dipole. I scroll down here, we've got a panel for setting up the solver. You can set some precision that it needs to run out to, and then a maximum number of iterations that it can run for before it terminates, whether or not it's reached the desired precision. There are a couple of different methods for doing this solve, but we'll just leave that on the default. You can refer to the Radia manual if you want to learn more about those. Mentioned there is parallelization for some of the routines. So you can see you can select serial or 5-core parallel execution. There's also an option if you have a really large problem, you can launch directly on the Cori supercomputer at NERSC. Assuming you have credentials and an account there, you can just select that and enter them and run it from this interface. All right, so I'll hit start new solve. This is a pretty simple setup, so this shouldn't take too long to do. You can see that it only took a few hundred iterations to get through. So now let's try plotting out that same field path that I was illustrating before and look at the field at the center of our gap. So I'm going to go to field paths, add a line. We'll just call it gap. We're going to have it run an X across the full width of our pole face from -100 to 100 millimeters. We'll have that centered vertically and at the center of the length of our magnet. We'll add a few more points to this just to better resolve that when we plot it. Once we click save and scroll up, we'll see there's now a new window that pops up that's going to get the requested points and plot them out. It does start out by default, this plot window is going to be in Z. In our case, we're looking at the field across X. So I'll go up to this pencil icon and change our plot axis to be X here. Redo that. And then, oh, it does do this sometimes, grabs the unsolved field. Normally, if you just run the solver again, is one easy way to fix this. That should automatically refresh. We'll see if this looks correct now. There we go. All right, so we know that our horizontal field on X and along longitudinal will be nearly 0 at the center of the magnet here, just by symmetry. So we'll uncheck those and just look at the vertical field. And you can see that indeed near the center, it's relatively uniform, close to -0.55 Tesla, but it drops off pretty quickly towards 0 as you get out towards the edges, kind of as we expected already. So now I'm going to jump back to PowerPoint and we'll look real briefly at a simple way to improve the field quality here across the pole face. So one common way to do this is by adding in shims. So you can see in this schematic here, this is again just the top right quadrant of our yoke. And we've got a little semicircular shim now that's been added onto the edge. These can also be rectangular, and that's often a lot more common just for ease of manufacture. But we'll look at this just as a nice example for using the extruded option that I alluded to earlier. So to do this, you can generate externally to Sirepo some point table, however you like. You can see I've got outlined here the points that make up just the pole and our semicircular shim here. You just need 2 points, of course, for any of the straight edges. And then where we've got this rapidly changing surface here for the shim, we use 25 points. And if you save these in a CSV file, that can just be directly imported into Sirepo. So I'm going to jump over and we'll try doing that now real quick here. So I've already got just pre-prepared, so I don't have to run through that whole thing again. The dipole setup, just minus the pole. So we'll add that in now. And go up to extruded and then drag and drop that here. We'll call this pole. And then in the geometry, we now have an option to select a file. And you see I already have the CSV file prepared here. Otherwise, you can click on new and this will open up your computer's hard drive. You can upload a file from there. So I'll select that. You do need to select a center point that just provides translation for all the points in the domain. And set that 50 and 110 vertically. And then sizes are all fixed horizontally since our points are all defined in X and Y in this case. And we're going to be extruding along the length of the magnet in Z. So that should match our 1 meter length. Go ahead and save that, and it should just take a couple of seconds and that'll pop up. And so now we've got just our first quadrant of pole here again. And if I go to our dipole group object, I can add that in and it will apply the appropriate symmetries there. And we can see the full pole face plus shims. If we go into visualization now, we'll take a look at this in the 3D viewer. Look down the beam axis and you can see, we'll zoom in here and take a look at the shims here. See that for extruded objects, there is actually an automatic segmentation process that's run, breaking up the surface into these triangular patches that'll automatically be a lot finer resolution. Here we've got this rapidly changing semicircle and then a lot more coarse out across the flat regions of the magnet. And we'll try real quick here. I'm running this. This might take another second or two since there is a lot of additional segmentation now in that pole face, but it's still pretty quick to run. And now we want to look at our field across that same path in the gap. So I'll just enter all these just the same as before. And save that. Let's switch over to plotting an X again. Let's see if this properly saved field state. Well, like it's hung up here. Normally you can refresh to fix this, but I'll just jump over here real quick. I already have this run prior to this, and we can see the result. So mention you can also set colors if you've got a lot of objects, just to make it easier to keep track of what's what. So this is what the field will look like now with these shims added in. If you remember what it looked like before, actually switch back here. We now have safely more flat profile here along the center of the pole face here. And we can directly compare this if we export that data, and you can plot these profiles against each other, like I've shown here. So this is again our field deviation quantity now plotted against the pole gap, or sorry, the pole width in millimeters. And we've got a little zoom in inset here, again, with this 10 to the minus 4 and 10 to the minus 3 bands. You can see that our shimmed pole face here in blue does achieve much better results in terms of maintaining field quality across the width of that pole face. So yeah, that brings us to the end of this demo, and if anybody has any questions.
All right, thanks, Chris. We have several questions in line here, and we'll just take them from the top. Question number 1, can you adjust the segmentation for extruded objects?
Yes, so there is an option to do that. Let's just jump back into here. If we can move the zoom part out of the way. If you go into our extruded object pole, and hit edit under the geometry section, there is this slider here for triangulation detail. And so this just provides a normalized version. As you go up in detail, this will obviously segment a lot more finely. And underneath, this is setting how the minimum angle and the maximum area of those triangles, well, they can be set to based upon the position of the slider. So that does give you some control over how that's set up.
This next question seems to be piggybacking on the same topic. And the question is, can we do the geometry extrusion along an arc?
Not that I am aware of. I think it just has to be defined along a straight line.
Thank you. Next question. In vacuum regions, does the accuracy depend on meshing of materials if the geometry of the material is properly represented?
Sorry, could you repeat that one more time?
Sure. In vacuum regions, does the accuracy depend on meshing of materials if the geometry of the material is properly represented?
It is going to depend upon that meshing. I guess it depends on how you define properly represented. Assuming that you've implemented the magnet design exactly as you envisioned, there is going to be a fair amount of dependence if you segmented it properly. That is going to then, if you have, for instance, around these corners here, you would probably want to have a lot finer segmentation as the field is changing direction rather rapidly. So if you only have a few segments here, you aren't going to fully capture that change. And that is going to be reflected when you actually take measurements of the field out even in the gap here. And depending upon the entire setup, it can be pretty sensitive to how you do that segmentation. So yeah, it does pay off to play with the segmentation some and make sure that you fully converged and are getting consistent results as you change the segmentation before trusting the simulation completely.
Thank you. Next question up is, can you export the geometry, either the Radia code in Python or in either an STP format or some other format for visualization?
So there are some options for export. There is a Python source you can do, which does dump out kind of a predefined template that will let you run these simulations on the command line. And you can kind of use that as a starting point to build up a simulation separately, just in a Python script. You can also export this Radia dump option. This Radia has a method for serializing the solve and the setup of these objects. And so if you select this, you can start up an instance of Radia, and actually it has an import function. Unfortunately, I don't remember the exact name of it, but you can find the import and load in one of these serialized dump files and then get access to an already solved model or run a solver on it. Should encapsulate the full geometry and state of the system, though you won't be able to edit any of the geometry at that point. And there also, outside of that, there are some options for, let's see, actually I don't have the window I wanted to show here. Let me see if okay. If you want to say, if you have field on path data that you've already run in the Sirepo interface, you can select this little cloud download icon, And you can also get that data in CSV format or STDS format, which is commonly used by the particle tracking code Elegant.
Okay, thank you. Next question is, can we change the shape of segmentation to cylindrical?
To cylindrical. I'm not quite sure how it look like. Generally, for most objects, you're going to end up just segmenting in cuts along the primary axes. And then for special cases, like the extruded objects, you do have this triangular segmentation that's set up. And that can be, I believe, applied to other objects. Not in this interface, but in general, Radia does have that capability to do that triangular segmentation.
Okay, thank you. And we're coming up on our time limit here, so we've got one more question that we'll answer. And then if your question was not able to be addressed today from our time limits, please feel free to join our Slack community. I put the link in the chat, and you can get additional resources or ask us further questions there. That's a great way to communicate with us. So last question for today is Radia intrinsically 3D, or can you also simulate reduced transverse XY or RZ geometries?
So unfortunately, it is just all intrinsically 3D. So the only way you can just kind of approximate 2D as kind of like I showed today by making one of your dimensions relatively long. Obviously, that is not a perfect solution since you are wasting a lot of computational time to make that happen. But yeah, all radius simulations do have to be in full 3D.
Okay, thank you. All right, that is our time for today. So thank you everyone for attending. And as I said before, we had a lot of questions lined up here. If we're not able to answer them live, please do contact us through our Slack community and we'll be able to help you with any questions there. Thanks again to Chris for the webinar, and we'll see you guys next month. Bye, everybody.